Hello everyone and welcome back. Now that we've started talking about torque, today I'd like to talk about net torque, which is going to be pretty similar to net force. However, before we get into that, there's something even more important I wish to discuss, and that is going to be Mr. M's torque rules. Now, the rules I'm about to give you were specifically designed for higher level torque problems, but they work for any level torque problem. So I'm going to introduce them now so you are familiar and comfortable with them when we get to the higher level. Basically put, there are 3 questions you should ask before starting any torque problem. This is, of course, after you have a drawing down so you can visualize the situation. Question number 1, is the system in equilibrium? So what that means is this: there is no linear acceleration and there is no angular acceleration. No change in velocity, no change in angular velocity. Now, the most common version of this situation is 0. 0 velocity, 0 angular velocity. In other words, the object is not moving and the object is not rotating at all. If you can recognize if the system is in equilibrium or not, this will help you out greatly. A big reason for that is if you recognize it's in equilibrium, that means there is no net torque and no net force. Net torque and net force are both 0. Now, I'm saying this as if you should know, but the truth is, you don't have to know. You can literally take a look at the problem, ask yourself this question: is the system in equilibrium? And the answers could be yes, no, or I don't know. In this case, I don't know is a perfectly valid answer, and we'll get into why in a little bit. So once you know if the system is in equilibrium or not, or you're not sure, you ask question number 2. Where is the axis? Now, right now at this level, this is a very simple question. It may even seem silly to ask. However, again, at the higher level torque problems, this question becomes extremely important. And whether or not you answer yes to question number 1 changes how you're going to answer this question: where is the axis? In most questions, especially at this level, the axis is given to you. With the wrench problem we did last video, it was where the bolt is. On a door, it's where the hinge is, and we're going to stick with that for a little while. But question number 2, where is the axis? Question number 3, how many non-zero torques exist? The big thing about this one is just because there's a force on your lever arm does not mean that force is producing a torque. Because remember, for a torque, you need a perpendicular force to the lever arm and you need a radius, a distance from the axis. So for that reason, the number of torques and number of forces may actually be different. Another side note of this, that means you may be dealing with torque and you may be dealing with forces in the same problem. Okay, the big special rule I will deal with in next video. So you're going to see this again. In fact, you're going to see this a lot because even though it may seem a little weird now, this little system is going to help you a great deal when the problems become much more difficult. In fact, I'm going to leave those rules in the lower left-hand corner here, and I'm going to reference them as I start doing problems. Okay, so situation 1. We're going to keep it simple for now. I have a door. This is an overhead view of the door, and there are 3 forces being exerted on the door. Now the question is going to be, what is the net torque on the door? And to do that, we're going to use a table to keep track of all these forces. And here's how we're going to label it. Force column, lever arm column or radius column equals the torque. All right, so this is going to help us keep track of all our torques and keep everything nice and neat, both for you and for anyone who is reviewing your work, which of course is extremely important on the AP exam. Okay, now we're going to ask our questions. First, is the system in equilibrium? Well, I have these 3 forces on this door. I know the numbers here seem pretty easy, but without doing any armchair math, I'm going to say, I don't know. I have no idea. I see 3 forces. I see some distances. There is no written description saying that the door is not moving or that it is moving or anything else. So I'm going to say, I have no idea. Besides, the goal is to find the net torque, and if it was in equilibrium, we'd already have the answer because it would be 0. 2, where is the axis? Well, it's a door rotating on a hinge, and the hinge is right here. So I have confirmed where the axis is. Again, easy right now, but this is going to be a very important question later on. 3, how many non-zero torques exist? Okay, I'm going to take a look at these in reverse order. In order to have a torque, you need a distance and a perpendicular force. Well, looking at C, I have a distance and a perpendicular force, that is a torque. For B, I have a distance and a perpendicular force, that is a torque. For A, however, I have a force, but I have no radius. So I have a force, but I have no torque here. So the answer number 3, how many non-zero torques is 2. There are 2 non-zero torques. That means when I start putting things in my table, I can completely ignore A. So I'm going to list my torques as B and C. I know torque A is 0, so it's not even going to come into play when looking for the net torque. Now, before I do anything else, I want to actually look at this column and ask myself, are these torques that I just found positive or negative? Now, as a reminder, you are following the unit circle, where counterclockwise is positive and clockwise is negative. Taking a look at B, B would swing around this axis counterclockwise. Therefore, B would be a positive torque. C would swing this clockwise. Therefore, C is going to be a negative torque. I'm going to put that in there right now because, again, the force directions don't matter. For example, an upward force here in this picture, this technically we'd say is a positive force, but it would rotate this door clockwise, which would be a negative torque. In this case, B swings counterclockwise and C swings clockwise. Okay, let's fill in the table. Force for B is 5 newtons. The radius for B is 2 meters. That would give us positive 10 newton meters. The force for C is 3 newtons. The radius for C is 3 meters plus the 2 meters to the axis is a total of 5 meters. And I get negative 15 newton meters. Therefore, my total would be negative 5 newton meters. This would be my net torque in this situation. Now, I'm going to add one more thing. Let's say someone grabs the end of this door, and I'm going to add a little extra distance, another 0.4 meters. There is a force on this door at the very end. My question is, how much force would it take and in what direction to keep that door from moving at all, to stop it from rotating? Now I've changed the question. And since I've changed the question, I'm going to ask these 3 rules questions again. 1, is a system in equilibrium? Well, the answer now is yes. I am flat out telling you there's a force exerted at this spot that is going to keep this door in equilibrium. It will keep the door from moving at all. 2, where is the axis? Well, that has not changed. It's still the hinge. 3, how many non-zero torques exist? Well, that's going to be 3 this time. And while we're here, there's something else we can do. If the net torque before exerting that last force is negative 5 newton meters, that would be a clockwise direction. Therefore, if this force is to prevent that, that means the force is going to be upward. It's one of the first things we could actually put on here. Now I'm just going to call this force D, and I'll put that in my table. Basically, it means this has to provide a positive torque. And since I know the system is going to be in equilibrium, this is no longer true. In fact, my net torque must be 0 newton meters. That's why I answered this question. If you can answer yes to the first question, immediately net torque is 0, which means the force from D has to provide a torque of positive 5 newton meters. So we now know the direction of force D. Now we need to know how much force D actually is. Well, all we have to do is find a force that makes a torque of positive 5 newton meters. The radius, or lever arm distance, is going to be the 2 meters plus the 3 plus the little extra 0.4 for a total of 5.4 meters. And since torque is force perpendicular times radius, all I have to do is take the torque, divide by this radius, and I'll get the force. And if you do that, you would get 0.956 newtons of force. That would be how much force someone would have to exert at the very edge of the door and in this direction to prevent that door from rotating at all. Okay, let's take the same idea and do it again from scratch. Here I have a revolving door. If you ever walked into a hotel, they very typically have these in the front. This swings around and allows people to go through. Now, let's say we have some kids playing in this door. There are 3 of them. I have kid A here. He is pushing with a force of 50 newtons to the right on this door. It is perpendicular to the door he is pushing, and he is 1.2 meters from the axis of rotation. Kid B is pushing with a force of 20 newtons upward, and he is 2.8 meters from the axis of rotation. Now, I have a third child. The third child is grabbing the door at the very end. And I'm going to say each door is 3.5 meters long. Now, these three kids are playing a game. These two are fighting against each other to try to rotate the door different directions. Kid A is trying to rotate it clockwise. Kid B is trying to rotate it counterclockwise. And Kid C is actually challenging both of them. His job is to make sure the door does not move. And we're going to say he wins. So this door is not moving anywhere. The question is going to be, how much force does Kid C have to exert on the end of this door and in what direction? If you want to try it, pause the video, write down this table on a sheet of paper, and figure it out, then hit play. So I'm going to start this one right now. I'm going to ask my rules questions first. Number one, is the system in equilibrium? The answer is yes, which immediately says my torque net is 0 Newton meters. Nothing is rotating. Where is the axis? Well, that's easy again. The axis is dead center. 3, how many non-zero torques exist? Well, A, radius, perpendicular force. B, radius, perpendicular force. C, radius, perpendicular force, but we don't know exactly what direction it's going to be yet. But we do know there will be 3 of them. A, B, C. Okay. Now, directions. Kid A. Kid A would rotate this clockwise. That is a negative torque. Kid B. Kid B rotate it counterclockwise. That is a positive torque. Kid C, unknown, which is fine. Let's see what we could find out. Force A, 50 newtons. Radius, 1.2 meters, which gives us a torque of negative 60 Newton meters. Kid B, force, 20 newtons. Radius, 2.8 meters, which gives us a torque of positive 56 Newton meters. So it's close, but right now, Kid A is winning. He is providing slightly more torque on the axis than Kid B is. Therefore, this would rotate clockwise. However, remember, the job for Kid C is to prevent this from rotating at all. Now, what I could do immediately is tell what direction he has to push, because his torque has to be positive. In fact, it has to be positive 4 Newton meters, because we need a net torque of 0. Positive direction is counterclockwise, therefore it has to be to the right from this above view perspective. The lever arm distance is going to be 3.5 meters, because again, that's how long I said the door was. So now all I have to do is, if torque is force perpendicular times radius, force perpendicular is torque divided by radius, 4 Newton meters over 3.5 meters, meters cancels, and you get about 1.14 newtons. So force C would be 1.14 newtons. So if you notice, I have my drawing. I ask my questions, which immediately starts giving me information like net torque is 0. The last question helps me lay out my table, keeps things nice and organized. All I have to do is plug in the information, make sure my net torque is 0, and backtrack. So the table is a great resource because the table is a great technique because it works in either direction. It could be used to keep track of your information and find the net torque, or if you know the net torque, you can work in reverse and find missing information in the table. And again, this makes it very easy to keep track of your work and very easy for someone else like a teacher or grader to follow your work as well. So just to show them one more time, is the system in equilibrium? Answers could be yes, no, or I don't know, perfectly fine. Where is the axis? We'll deal with the special rule next video. How many non-zero torques exist? That's how you know how many torques to put in your table. All right, I mostly wanted to use this video to introduce net torque and to introduce this little system to help you out. So I'm going to end it here and start to get into some details next time. Have a good day. This is Mr. M signing off.